Hello, everyone. My name is Najim, and my teammates are Alan, Benjamin, Samuel, and our project is on 2015 US police killing. All right, so the project focuses on the analysis of 2015 police killings, aiming to provide a data-driven perspective on the incident to better understand the factors surrounding police-related death and uncover potential patterns that may inform policy decisions. All right, so key goals. We want to understand the contributing factors. So examining relationships between race, age, armed status, socioeconomic conditions, and analyze any correlations with the likelihood of police-related fatalities. We also want to explore trends, so racial and ethnic disparities, geographical patterns such as states and regions within the highest incidence, and socioeconomic indicators such as education, poverty, and urbanization. All right, so data and tools. So our data set is the 2015 US police killings. Our key attributes are demographics, which include age, gender, race, and ethnicity. Our incident details include armed status and cause of death and location. Our socioeconomic indicators are poverty level, education, urbanization rate, and median income. And lastly, our tools for analysis would be data manipulation, which is pandas, visualization, which includes Seaborn, Map, Plotlib, and Plot.ty, and geospatial analysis, which is GeoPandas, and lastly, machine learning models that include scikit-learn, XGBoost, and random forest.
All right, this is our visualization. We're going to ask 5 questions, starting with which race ethnicity faces the most deaths by police, and how does being armed and race influence the outcomes of the police killings? And our third question, which states report the highest deaths, and what is the role of poverty and education levels? And our last question is, what are the common cases of death by race? So let's move on to our first question, which is which race or ethnicity experiences the most deaths by police? And our results show that 50.8 of the cases involves white people, which is the highest among other races slash ethnicity, followed by 28.6% of Black people, which is the second highest. And going to our second question, does being armed combined with race influence the outcomes? And we found that white had the highest number of cases of police deaths in 2015 when armed. And you can see in this graphic, firearms are the number one cause of death. Our third question is which states report the highest police-related deaths? And the results show that looking from the heat map, it shows that California had the highest number of police-related deaths according to the darkest shade on the heat map, followed by Texas. And question 4, how does socioeconomic status play a role in these police deaths? And through our findings, we saw that lower education levels might be more strongly associated with police-related deaths than poverty levels. While there are some clustering of police-related deaths in moderate poverty areas, the data does not conclusively show a direct relationship between the extreme poverty and police-related deaths. Instead, the educational factor appears to be more significant. And our last question, what are the most common cases of death by race? And as we saw in the second question, we saw that firearms, gunshots, were the most common cases of death across all racial groups, being white having the highest number of deaths, followed by Black and Hispanic Latino groups.
So the goal of our machine learning analysis was to classify whether a person killed by police was armed or unarmed. This is framed as a binary classification problem, with armed and unarmed as the two classes. Understanding the factors contributing to armed versus unarmed status provides us invaluable insights into how the systemic trends can help inform policy recommendations. We also utilize features such as race, age, location and socio-economic indicators like poverty and education to train our models, aiming to uncover patterns that could address these critical issues. So our analysis faced several challenges, primarily due to an imbalanced dataset. Most cases involve individuals who were armed, which led to the model performing poorly when predicting the minority case, which is unarmed cases. Additionally, strong correlations among features like race and socio-economic indicators complicates our ability to isolate their individual impacts. Finally, limited data points for minority classes also increase the risk of overfitting, which we had to carefully manage. To address these challenges, we tried to implement several strategies. First, we use a data balancing technique like SMOTE, SMOTE, for oversampling and undersampling the majority class. Feature engineering also played a critical role. We tried to normalize the features and also remove the multi-collineal variables to enhance model interpretability and accuracy. Lastly, we explored weight balancing for classes, penalizing incorrect prediction to improve performance.
So the models we implemented were XGB boost, random forest, gradient boosting, and ISO forest for anomaly detection. On the right, you can see that we used the precision recall curve to analyze the performance of our models because our data set is imbalanced. Some of the problems we encountered was that our data is imbalanced, meaning that it's going to perform really well on the cases that have a lot of entries, like the ARM cases. The things we tried for our machine learning project was oversampling, undersampling, PCA, weight balancing for classes, even simpler models such as SVM. For the first model, we used XGB boosting. Out of everything we tried, XGB boosting without oversampling or undersampling performed the best, achieving 37% in F1 score, 0.40 in precision, and 35% in recall. Next up is random forest. The best random forest model was also without oversampling or undersampling. The scores are almost similar to the one we previously had from XGB boosting. Then gradient boosting was that we required oversampling for to get better performance out of it, and it did worse in predicting more false negatives, but actually got predicted more on ARM cases. And then lastly is the isolation forest, which is an unsupervised algorithm used to detect anomaly or rare cases. For this instance is the unarmed cases. We trained it on the entire data set and then analyzed the performance using a confusion matrix, and it did not perform as we hoped it would, doing very poorly with only 2 out of 23 fraud unarmed cases and very high amount of false positives and negatives.
So our results revealed key insights on XGBoost and random forest models, and that they performed similarly while gradient boosting excelled in predicting unarmed cases but struggled with armed cases, resulting in more false negatives. Isolation forest was the least effective, missing about 87% of unarmed cases. Overall, the small dataset and class imbalance limited the model performance, highlighting that there's a need for more data to achieve meaningful predictions. So we tried to compare with the original dataset. We switched it to the original Guardian datasets, and it shows that there was an improved results. The dataset contained 2.4 times more entries than the initial one, which led to 20% increase in their F1 score and about 2 to 3 times better precision. However, recall scores remain constant. This change underscores that the critical impact of data quality and quantity in machine learning tasks, especially for imbalanced datasets. Thank you. And yeah, any Q&As?